In our last video, we were looking at applications of integration related to work and force and mass. In this particular one, we again want to look at work and we want to look at the force created by gravity when we're trying to pump a liquid, water, gasoline, or what have you, out of some kind of container. So again, we're going to be applying some kind of force to lift the liquid, and it's going to have to travel through a distance in order for work to be done. So now what we want to do is we want to kind of look at these types of problems. Now, the textbooks don't typically get into this. In most tanks, the pipe is actually fixed at a certain depth, but we're going to consider ours to be floating on the surface of the water so that each layer of water moves a different distance. And this will create a different equation for us when we look at work. So what we're talking about here is we're talking about some kind of container. This is a water tank for cattle or horses. And you can see right here, it's basically a right circular cylinder. And this is another water tank for a house. This is also a right circular cylinder. The side is cut away so that you can see the water on the inside. Now, this pipe right here is the outlet pipe. And notice that it's not at the upper level of the tank. It actually extends above the tank. So that has to be taken into account when you're computing the work done. Now, if the water level was here, it would have to move to the top of the tank, then to the top of the outlet pipe. And the work required to do that has to take this full distance into account. Now, if we were moving water out that was at a lower level, it would have further to move just to get to the top of the tank, plus the height of the pipe above the tank. So this would create an instance of more distance, resulting in more work to move the lower layers of water. So these situations also depend upon the size and shape of the tank, because that affects the volume. And the volume, of course, when multiplied by the density, gives us the mass. And the mass is acted on by gravity, which of course gives us the force. And then we apply the force through the distance that it is moved, and that gives us the work. So the force required to move the liquid depends on the height of that level of liquid and the distance we have to move it through. We're going to slice our water or gasoline or whatever it is into layers of liquid. So they're going to be stacked one on top of each other horizontally. And we're going to move individual ones out. Now, why would we think of doing it that way? Well, again, because the work depends on the distance in which it's moved, we have to have a constant distance. So we create a very thin, now this is way thicker than it should be, but we create a very, very thin layer of water. Now this one is in a circular cylindrical tank, so this one has layers that are actually also circular cylindrical tanks. So they do have a tiny amount of height to them, which we'll call dx, of course, or dy. If you want this to be the y-axis, you can call it dy, or you can label it the x-axis and call it dx. It doesn't matter. And this little layer of water has to move from where it is to wherever the outlet pipe is located. And that's the distance it has to move. If the outlet pipe is at the top edge of the tank, then it moves from here up to here. If the outlet pipe is above the top edge of the tank, then it has to move to the top of the tank and then further up to get out of the outlet pipe. So each little layer of water is going to move a different distance. So what we're going to do then is we're going to assume that gravity is acting constantly on each individual little layer of water. So we're going to compute the mass by finding the volume of a single slice or a single layer of water. So we're going to find the volume of it and multiply by the density of that liquid. Water would be 1,000 kilograms per cubic meter. And then once we multiply the volume of the layer by the density, we'll have mass. Then we take the mass and we multiply by gravity. That gives us MA, which gives us the force. And then we have to move it through a distance. So we'll have to compute what the distance is that it needs to move, which means that we'll need some kind of axes, some kind of X and Y. Now you can think of this like this toy that you see on the left with this toddler. She's stacking little discs on top of each other. They're all the same size and all the same shape, and they're very, very thin, and she's stacking them one on top of each other. It's sort of like stacking very flat plates. So each little plate represents a single layer of this water that we're going to move. Now, they're not truly two-dimensional. They're still three-dimensional because they do still have a little bit of thickness to them. And that thickness is going to be our dy or our dx, depending on what you want to label it as. So it's this distance that you see right here. From here to here, this is going to be our dx or dy if you prefer to call the vertical axis y. So what we're doing here is we're setting up kind of an origin. Now, the textbook likes to set the origin up at the top, and you'll see right here they have x equals 0, and they've made down a positive direction, and they measure it that way. I tend to do it differently because that always confused me in physics. I like to put the origin at the bottom, and then up, of course, is positive, and that makes it a little bit easier for me to figure out. The problem with putting it at the top of the tank, if the outlet pipe is above that, then you're going to have both positive and negative distances, which can be a little confusing. So I don't like to put mine at the top. Instead, I put mine oriented down here at the bottom. And so I would call this the x-axis, where this would be my origin down there at the center of the base. And so that way, all of my distances are strictly positive, and I don't have to worry about negative x values. So you can see here again that I've oriented it at the bottom, and I've got this vertical axis through the center of the tank. Now you can either call this x or y. If you call it y, then you're going to have y sub i's, and you're going to have delta y or dy. If you call it x, then you have dy or delta x. Now, when we move these out, we're assuming that the gravitational force on each layer, because it's so very, very thin, is roughly constant. And then we want to see how much work is done. So let's put all the formulas that we talked about in the previous video together, and let's build this formula in order to move the volume of water out of the tank. We know that work is given by force through a distance, so force times distance. Force is mass times acceleration, so work would be mass times acceleration times distance. We know that acceleration in this case is gravity because lifting the water out is fighting gravity. That's the force we're having to exert, is to overcome the acceleration of gravity, which is pulling it down. And so we can replace the A with G, so we get mass times G times distance. Now, when we come down here, we need to be able to find the mass, and this is where the difficulty in these problems comes in. We'll have the density of the liquid. That will have to be given to you. We know the density of water is 1,000 kilograms per cubic meter. Gasoline is less than that. It's not as dense as water is. And this is per unit measure, length, area, or volume, depending if it's 1D, 2D, or 3D. Now, in our case, it's an actual tank, so it's three-dimensional, so we're going to have volume. And we're going to have to compute the volume of the little slice of water. Now, the slice of water is going to take on the shape of the container. So it could be rectangular, it could be circular, it could be all kinds of shapes. Typically, what we see, though, is rectangular and circular, those two types. So now we put all of that together, and we have that the volume of a single water layer for our right circular cylinder tank, the one we've been looking at, is going to be the area of the base, pi r squared, times the thickness or the height of that layer, which is dx. So again, looking at our picture up here, from the center to the edge is r. So the volume of that little slice of water is going to be pi times r squared times dx, or delta x. And delta x is the thickness of that layer. And it's very, very thin. And of course, you know what we're going to do. We're going to partition the water into a lot of little layers. We're going to allow the thickness of each layer to go to 0 and the number of layers to go to infinity. We're going to get a Riemann sum. We'll take the limit of it as n goes to infinity to get the definite integral. So let's take a look now. We've got the volume of the water layer, which is pi r squared dx. And we know that the mass is given by the density times the volume. So we take density and multiply by pi r squared dx. So this now gives us the mass. And then we have to multiply the mass by the acceleration. So the mass times the acceleration is due to gravity. So we have rho times volume, that's our particular mass, times gravity. And our volume is pi r squared dx. And notice that we kept the dx at the back. It's actually a part of the volume, but we kept it at the back because that's where differentials go. All right, so we have rho pi r squared times gravity times dx. Now that gives us the force. Now we have to think about the distance through which we're going to move it. So we have this distance that has to be moved through. So this will be a distance of d. So that gives us the mass, density times volume, which is rho times pi r squared dx in our case. And then we multiply by gravity to get the force. And then we multiply by the distance it's moved to get the work done. Now it's the force that's varying, not the distance through which it's moving and that sort of thing. It's the force that's varying depending upon the level of the water. So when we're looking at these, we can think about it this way. Now in this one, I've drawn the outlet pipe at the edge of the top of the tank. And let's say that the tank itself is 10 meters tall. Well, then this particular layer of water right here is at a height of x based on the axis that I've drawn where it comes down to the bottom. So the origin is down here at the bottom, and that makes this vertical distance x, or if you want to call it y, you can call it y. So this is that distance. Now, how far does it have to move? Well, the entire tank is 10 meters high, but the layer of water is already at height x. It doesn't need to move x. It's already at x. It needs to move what's left of the distance between 10 and x, or 10 minus x. So that would be the full distance minus this distance, which gives us that distance. So this distance right here is going to be the 10 meters minus x. All right. Make sure that you remember that it's not x. It's going to be 10 meters minus x. Now, we're going to set up the integral, and you'll see that instead of putting in limits of integration, I've put in two phrases. You cannot move water you do not have. If the water in the tank only goes up to 6 meters, then you cannot move water beyond 6 meters. So this is going to be the lowest layer of water, the height of the lowest layer of water you're going to move out of the tank. And the upper limit of integration is the highest layer of water you're going to move out of the tank. The maximum value of the upper limit is the height of the water in the tank. It can't go above the level of the water in the tank. This is not going to be the full height of the tank necessarily. It's the level of the water you're trying to move. That's what the limits of integration are. And then the rest of it becomes pi, or not pi, rho times pi r squared times g times 10 minus x dx as we take the limit and go to infinity. Now, in this case, because we're talking about water, we know the density is a constant. It's 1,000 kilograms per meter cubed. We know gravity is a constant. It's 9.8 meters per second squared. And pi, of course, is a constant. And in our case, because it's a circular cylinder, the radius is always a constant as well. That's not always going to be the case. Sometimes the radius is going to depend on something else, and we'll have to take care of that. So in this particular case, it's going to make the integration relatively straightforward, right? We need a more general formula because we're not always going to have circular cylindrical tanks where the radius is always the same. So what we're going to do instead is we're going to let A of X represent the cross-sectional area of the water slice. So we're going to think about the water slice, whatever shape it has on the surface, and then it's got a thickness to it. So we're going to find the area of whatever shape it has on the surface, and we're going to multiply by the thickness, and that will give us the volume. Now the thickness is dx, and the area of the surface, of course, is A of X, and it may depend on the height. It may be in something that's cone-shaped, so it could be something like this, or it could be something, well, I guess it would be like this. So if you're looking at it, each little layer would be at a different height, and each little layer is going to have a different radius because this is cone-shaped. So the radius is not constant, it's getting smaller and smaller as it goes down. So when we're looking at it, we have to take into account the fact that the area function of the surface of the water layer may not be a constant. It was for the circular cylinder, but that won't be the case for all shapes. So we take this, which represents the volume right here, and then we're going to multiply it by the density. So we have A of X and dx, which gives us volume, times rho, which is the density. That gives us volume, times gravity, times some function of X, which is the distance that we need to move. It doesn't need to move the X distance it's already at. It needs to move from the height of the outlet pipe minus that distance. So now what we have is an example. So we want to work through this example. I have several different examples for you, and I've kind of talked you through these. So first we want to find the work done to pump the top 3 meters of water from a right circular cylindrical tank. It contains 8 meters of water. So I'm not moving all the water out. I'm moving the top 3 meters out. So from 5 meters to 8 meters. Now, just like in the spring, do you think it would be more work if I moved the bottom 3 meters out? Yes, of course. Why? Because they've got to move a further distance. So again, work is forced through a distance, and the bottom 3 meters are further away from the outlet pipe. So they would have to travel further. So even though I'm moving the same volume of water, it would take more work because they're further away from the outlet pipe. Now, the outlet pipe on this one is not at the top of the tank. It's 2 meters above the top edge of the tank, and the tank itself is 10 meters tall and has a radius of 4 meters. Let me share my screen with you and we'll get started. So the first thing we want to do is draw a picture and label everything we can think of. So I have my tank, which looks like this one on the left, and my tank happens to be 10 meters tall. So from the top edge of the tank to the bottom of the tank is 10 meters. Now the outlet pipe is located 2 meters above the top of the tank. So the outlet pipe is a full 12 meters from my origin, which is down here at the bottom center of my tank. So the total distance from the origin of the outlet pipe is 12 meters. Now the water only goes up to 8 meters. So from the bottom of the tank, where the origin is located, up to the top layer of water is 8 meters. I cannot move water I do not have. You cannot have a limit of integration above 8 meters. You don't have any water above there. We can only move water we've got. We want to move the top 3 meters of water out. It would take more work to move the bottom 3 meters out or the center 3 meters out. Now, what we need to do is we need to find the volume of one of our water layers. So we look at the water layer, the surface of it is a circle, and we know the area of a circle is given by pi r squared. Now, we were told that the radius of this tank is 4 meters. And because it's a cylinder, it never changes. It's always going to be 4 meters. So every layer has the same cross-sectional area. which is going to be 16, and that should be square meters instead of just meters. So we have 16 meters squared times pi. All right, now I like to keep my units in there because I was a physicist before I was a mathematician, and it just helps me to stay honest and make sure I've set it up correctly. Now the width of the layer is going to be delta x or dx because I'm calling the vertical axis x. If you call it y, you'd be using dx or delta y. So the volume of the water slice is 16 square meters times pi times dx. That's the volume of one slice. Then I'm going to take my one slice and I'm going to multiply it by rho, which is the density of water, and that will give me the mass. And then I'll take the mass and I'll multiply by gravity, and that will give me the force. Now I need to talk about the distance through which it's moved. So let's take a look back at our picture again up here. The current layer of water is at height x. So you can see that right here. So we've got this height x that's right here, and it needs to move from here up to the top of the tank and then 2 more meters to get out. So what is the distance it needs to move? The outlet pipe is at 12 meters. It's already gone x, so it needs to go 12 meters minus x. So the distance that it's moved is a function of x and given by 12 meters minus x meters. So now we have this expression right here, 12 meters minus x meters. Our limits of integration are given by the water levels that we're moving. The lowest water level I'm moving is the top 3 meters. So 8 meters minus 3 meters is 5 meters. And then the top layer that I'm moving out is at 8 meters. So I'm moving from 5 meters to 8 meters. And now I can go ahead and set up the integral. From 5 meters to 8 meters, density times gravity times pi times the 4 meters squared. That's my 16 meters squared times pi. That gave me my area times dx gave me volume. And then times the distance it's moved, 12 meters minus x. Notice that rho, the density, is a constant. It can be pulled directly out. Now, I always leave mine rho g until I'm actually at the last step, and then I put in the numbers, because otherwise you do a lot of writing and rewriting and rewriting. So I leave these as rho times g until I get to the bottom. G, of course, is 9.8 meters per second squared, and we found the cross-sectional area to be 16 pi meters squared. The only thing that depends on x in this problem, this is not always the case, but in this problem, is the expression for the distance through which it's moved, 12 meters minus x. So that's the only one you have to integrate. So go ahead and pause the video, integrate, and then turn the video back on and let's compare. So let's go ahead and take a look and see how you did in setting up your integral. So there was the integral that we had. When you integrate, it's pretty straightforward. It gives you 12 meters times x minus x squared divided by 2, evaluated from 5 meters to 8 meters. Notice that the rho g I just left as rho times g. It's faster to write than writing it out, times 16 pi meters squared. I'm keeping the units there. Then I substituted the limits of integration here, and this gave me 33 divided by 2 meters squared. Now notice that if you keep the units in there, you do get meters times meters, which gives you square meters, and this comes up square meters, and square meters minus square meters is square meters. Now when you plug in the actual values for the density and for gravity, notice that you've got a meter cubed down here, you've got meters squared and meters squared, which gives you 4 meters, and 3 of them will cancel with what's in the bottom. And then you've got another meter up here, so that gives you meters squared in the numerator times kilograms divided by seconds squared. So the final answer that you see is this amount right here, and the units are kilogram meters squared per second squared, which is another way of writing joules. This is a Newton meter, which is also a joule. And you can see the value right here. I tend to leave pi as pi because it's exact. If you want an approximation, of course, you'd multiply by some approximation of pi. Let's take a look at another example. This one is a conical tank. So this one is more like the tank that we have right here. So it's shaped like a cone. So you have this cone here, and you've got the top. Now, you know that every cross section is going to be a circle like the top of the cone, but they're going to get smaller. The layers are going to get smaller as it goes down to the bottom of the tank. So we know that the cross-sectional area is varying with the height of that layer. So it varies with x. So a of x is not a constant this time. It varies. Now we want to pump all the water out of the tank. The outlet pipe is located at the top edge of the tank, so it's not above the tank. The tank is 15 feet tall, so the outlet pipe is at 15 feet. The water is at depth 10 feet. So the water goes from 0 feet up to 10 feet. All right. And the top of the tank has a radius of 10 feet. So we have 10 feet of water that we need to move out. You cannot have a limit of integration above 10 because you don't have any water above 10 feet. You only have water from 0 feet up to 10 feet. So our limits of integration will go from the bottom to the top layer of water, which is at 10 feet. Now we want to draw a picture and label everything. And we're going to put in the vertical axis and the origin. And we're going to see what kind of shape our little cross sections have. So here's what we've got. We've got a conical tank with the apex down. We can see the radius of the top of the tank is 10 feet. But the radius further down is not going to be 10 feet. It's going to be much smaller than that. We know the tank itself is 15 feet tall, and the outlet pipe goes out right at the top edge of the tank. Now, right now, we know that we have water between 0 feet and 10 feet. Obviously, this is not to scale. I should have colored in a little bit more. So we want to figure out what our little slice of water is going to look at. So I've got a little slice of water, which is going to be right here. And if you look at that, what shape does the surface of the water have? Well, the surface of the water is a circle. And I know that the area of the circle is pi r squared, but the problem is my r keeps changing. If I were to come further down and I were to look at this spot right here, I would have a different radius. So this would be some different radius, R2, all right, which would not be the same as R, and both are not equal to the 10 feet at the top of the tank. So as I go further down, the radius is getting smaller. So the radius is depending upon this height here from the bottom, which we're calling X. So the height of my particular layer is X, and the radius is a function of X. It depends on the X value. What we're going to use in order to compute these is similar triangles. So let me show you how to set up the similar triangles. So you can see here I've got two layers of water with an R1 and an R2. They each have a very narrow width to them or depth to them, which is dx. And you can call this H1 and H2. H1 goes up to the slice that has radius R1, and H2 goes up to the slice that has radius R2. Now, if we look at this and we cut half of the cone away, you can see over here that we actually have a right triangle. The top of the tank is flat and it's perpendicular to the axis of the cone. And so this gives us a right triangle right up here at the top, right there where you can see it. So this leg here is going to be 10 feet, the radius. The height of the entire tank is 15 feet. And I know I've got some slice of water right here, which is my R1. And the depth that it's at, my X value, is H1. So I want to know how it depends on that. Now, H1, of course, is just representing the X value for that particular slice of water. So when I'm looking at these two triangles are different sizes, but they are similar. They both have a right angle here, and they share this angle at the bottom. And if two of the angles in the triangle are the same, then all three have to be the same, which means that all the angles are the same, therefore they're similar. Now, that doesn't mean that the sides are the same length, they're obviously not, but they are proportional. So we can set up a proportion to find the relationship between R and H1, which of course is our measure for X. So now we're going to set up our proportion, which is right here at the bottom. Now you can set it up a couple of different ways. This is just one way. I'll show you another one. I can say that R1 over H1. So I'm measuring the radius over the height of that layer of water, has to be proportional to the radius of the whole tank over the height of the whole tank. Notice I've got both the radii on top and I've got the heights on the bottom. And then this tells me that R1 is equal to 2H1 over 3. And since H1 represents X, really what I have is that the radius is 2X divided by 3. So I have a relationship between R and X. Now I said there's more than one way to set these up. You could also write R1 divided by 10 feet, where you put both of the radii together, has to be proportional to, well, I started with the smaller one on top, so I need the smaller height on top. So this would be H1 over 15 feet. And if you cross multiply and work that out, you're going to get exactly the same thing because it's essentially the same proportion, just in a different format. So hopefully this makes sense to you, how we use similar triangles to get a relationship between the sides. We now know that the radius depends on the height of the water layer. The height of the water layer is X, so we have 2X over 3. Now remember that the surface of the water itself is a circle. So we're going to take the radius, which is 2X over 3, and we're going to square it. So 2/3 X squared, and then multiply by pi. So that gives us 4/9 X squared times pi. And then we multiply by dx, the differential, to get the volume. So this is the area here multiplied by the height of the water slice, which gives us volume. So this is our volume right here. Now we want to take the volume and we want to multiply by the density, and that will give us the mass. Now the bottom layer, of course, is at 0 feet, and the top layer is at 10 feet. So those will be our limits of integration. And now we need to figure out how far does each water slice move. Well, again, we can look back at our picture up here. This water slice is going to move a distance that is the difference between 10 feet and H1 feet. So this is going to be 10 minus H1, or 10 minus X. 10 feet minus X. So our distance formula is going to be, or is it 15 feet? 15 feet, sorry, the height of the tank is 15 feet. So we have 15 feet minus X. So now we have a little bit of a problem. This is in feet. And our density that I gave you earlier was, I gave you the density of water as 1,000 kilograms per cubic meter, and this is in feet. Those don't mix well. Now we could convert, and that would be a nightmare. But we can instead use what's called the weight density of water. Weight density is rho multiplied by g already. So we already have the density multiplied by gravity. So it gives us rho and g in one fell swoop, and that's 62.4 pounds per cubic foot. So this is the weight density of water in the English system of measurement. So this gives us rho g. Now, rho times the volume will give me the mass, and the mass times the gravity gives me the force. So I need to multiply this rho g then by the volume in order to get the force on our particular slice. And we're ready to go ahead and set it all up. So let's take a look at it. So we're moving water from 0 feet, bottom of the tank, and the top layer of water is at 10 feet. And then we have rho g, this is going to be the weight density, and then we have pi, and we found that the radius was 2/3 x, so 2x over 3, and we square it. We got 4/9 x squared pi. And then we have to multiply by the distance through which it's moved, the 15 feet minus x dx, right? So go ahead and pause the video, work out the calculus, and then turn the video back on, and we'll compare what we got. So let's see how you did. When we set this up, we have rho g, which of course is the weight density of water. And then we have the cross-sectional area times dx, that gives us the volume. And then the distance through which each layer of water is moved is 15 feet minus the height of the water layer, minus x. So when I squared this, I got 4x squared over 9. Rho g and pi are all constants. I pulled them out. The 4/9 is also a constant, so I pulled it out. And then I distributed the x squared across the distance. And that gave me 15 feet x squared minus x cubed. And then when you integrate that, you're going to end up basically with 5 feet times x cubed minus x to the 4th over 4. When you divide by 3, 15 divided by 3 gives you the 5. Then you plug in the limits of integration. Notice when you plug in 0, they're both going to 0 out. So you really have it at the upper limit of integration. Evaluating this gives you 2,500 feet to the 4th power. Notice feet times feet cubed gives you feet to the 4th, and this is feet to the 4th. If your units don't work, something is wrong, right? And then, of course, we go ahead and we write out what rho and g are. So rho g is the weight density of water, which is 62.4 pounds per cubic foot. Then we have pi and the 4/9 times 2,500 feet to the 4th. Feet to the 4th divided by feet cubed gives me feet, and that gives me foot pounds. And I end up with 208,000 pi divided by 3 foot pounds, which is, of course, an enormous amount of work done. That's a lot of work to move water. Water is extremely heavy. So we want to take a look now at one last example. This one is quite a bit more difficult. It also uses similar triangles, and it's a little challenging to set up. So I thought I would work through this one. We have a horse trough, like an old-fashioned, Western movie horse trough, and it's shaped like an isosceles triangle on the ends, right? So I'll show you a picture of it in a second. The outlet pipe is located at the top edge of the trough, and the water is initially at a depth of 2 meters. Now the trough itself is 4 meters wide, 6 meters long, and 3 meters deep. So we want to draw a picture. We want to label everything. Remember to put in the vertical axis and the origin. And then we want to figure out what shape the surface of our water layers are going to have so that we can compute the volume. Now, this is what the tank looks like when you're looking at it here. So it is this kind of shape, and I've made one out of cardboard just so I could sort of indicate to you what it looks like. So I've cut away this end so you can see inside. This end is an isosceles triangle, so it's made out of cardboard, and the water goes in the top. Now, the problem is that the water layers, if you put the water layer in here, so this is a water layer, you can see that it's actually a rectangle, right? The surface of the water is a rectangle. But the problem is, the further down you go in the water trough, the smaller the rectangle gets, unfortunately, which means that our cross-sectional area function is not constant, which means that it must depend on the height of that particular water layer in the trough. So we need to figure out an equation for that cross-sectional area of the surface of each of the little water layers. And that will enable us to figure out how to find the volume by multiplying it by the differential dx. Now, as we go down, again, these boxes, these tiny little, very, very thin boxes that represent the layers of water, the width is getting smaller as it goes down. But the length of it is still 6 feet. So this is still 6 feet, but the width of it, that's getting smaller as it gets lower. So we need an expression for the width in terms of the variable x. So we're going to take a look at the end of the trough, which is an isosceles triangle. And remember, it is 4 meters wide, so the whole trough is 6 meters long. But the isosceles triangle part is 4 meters wide. The water is at a depth of 2 meters, so the water comes up to here. And the trough itself is 3 meters tall. Now, this red rectangle that you see here represents that slice of water. So this is the end view of a slice of water. Now, we want to cut this isosceles triangle in half. And notice that this width here, part of this width, which I call W sub I, is not actually the width of the water layer. 2 W sub I would be the width of the water layer. W sub I is half the width of the water layer. But I want W sub I because I want to cut this and create a right triangle. And in the right triangle, then I can create similar triangles. I could do it with the isosceles as well. So when I'm looking at this, if I cut half of the top, then instead of 4 meters, I have 2 meters. So this measure here at the top is 2 meters. I don't know what this measure is. That's what I'm trying to find, the length or width rather of that pink box. That's W sub I. I know it's at a height of X sub I, and I know the entire tank is 3 meters tall, but that gives me my similar triangles. So I'm going to go ahead and highlight the 2 triangles for you here. So here's one of them coming here, and the other one is here. Right, so you can see the 2 similar triangles. Notice they both share a right angle here in the upper right corner, and they share the angle at the bottom. So they have 2 angles the same, so all 3 are the same, so they're similar. So the lengths of their sides must be proportional. So we set up a proportion, and in this case, I want to find W sub I. So I put W sub I in the numerator, and then I divided by X sub I, which is the height of that water layer. And then I'm going to set it up similarly. So taking the horizontal measure of the tank would be 2 meters over 3 meters. And this tells me that W sub I is 2X sub I over 3. Now, the actual width of the water layer is twice that, because remember, I've got to go all the way across. So the actual width of the water layer is 4X sub I over 3, or 4X over 3. So let's go ahead and start setting up the integral by gathering information. We want to move all the water out. We have water from 0 meters to 2 meters. We set our origin at the bottom of the tank. The cross-sectional area, it's a box, so it's length times width times height. It's 6 meters long. The width is 4x divided by 3, and the height is that tiny, tiny little depth of it, which is dx. So when we multiply that out, we get, what is that, 8 meters x dx. Oh, I'm still using pink, so I should change that up. 8 meters times x dx, right? So that's our cross-sectional area. Well, it's actually, this is the cross-sectional area, and this gives us the volume. All right, so I should probably fix that in my notes. Now, how far does each water layer move? Again, the total tank from the bottom to the top is 3 meters, and the outlet pipe is located at the top. So the outlet pipe is 3 meters from the origin. It's already at a height of x, so we want to move 3 meters minus x. Now we can set up the integral. So we integrate from 0 meters to the top layer of water, 2 meters, rho times g, rho times the area, there's our 8 meters x, and then the differential dx gives us volume times density, which is mass. Mass times gravity is force, and force exerted through a distance 3 meters minus x gives us the work done. So we'll go ahead and pause the video, work out, and then turn it back on and we'll compare our results. So you can see that I went ahead and just put everything in right here. Notice that we did have this X here. The 8 meters is a constant, rho is a constant, G is a constant. They can be pulled to the front. But X times 3 meters minus X, those all depend on X. They have to stay in the integral. And so that gives me 3 meters X minus X squared. And when you integrate after doing all the work, you end up with 261,333 and a third joules. All right. So this is the last example that I wanted to show you on how to pump liquid out of a tank. And this would apply whether you're pumping gasoline out of a tank at a gas station or out of a truck if you're transporting it, or milk out of a truck, all kinds of situations where you need to pump a liquid through a distance fighting gravity. So in the final video, we'll take a look at what's called hydrostatic force and hydrostatic pressure. I hope you'll join me for that video.